All right, we'll go ahead and get started. Let's see, this is, well, I assume everybody's in the right place, but this is Applications of Deep Learning. And my name is Jeff Heaton. I'll be the instructor for this class. Let's see, I think I'll go ahead and just start by going through the syllabus and other information first, and then I just want to make sure everybody's here, so I'll go through the role and start to learn your names so that we'll do that just in case anybody else is about to walk in the next few minutes. So all of the information that you'll need for this class, the syllabus, everything, I really don't print stuff out much because everything's on Blackboard. So everything that you will need for this class will be in Blackboard. I have that all set up. You should have all received an initial announcement from me that went through that. And I can see some of you have even answered my initial survey questions just to let me get to know you guys a little bit better. So the assignments, which will also be submitted through Blackboard. So let me show you that part first. There's not a whole lot of stuff that I've added to Blackboard, so you will be able to, let me go into the class first. So all of the course documents, I will add those here. The syllabus is there, so if you want a hard copy of that, you can certainly print that out. It's just a PDF. It shows you the schedule for the semester, or at least as I have things planned for now. There is also a course website. What I place there is all of the links for the class. So all of the material that we'll go through, sort of like PowerPoint, except we're going to use something called Jupyter Notebooks or Python Notebooks. So this is very interactive. It's a little bit MATLAB-like in the sense that you have code intermixed with graphics, intermixed with everything. So I will be able to, so if you see some code that I have on one of these slides and you want to ask me, well, Jeff, what happens if that was done that way? Well, I won't necessarily know, but I can change the code and literally run it right here. So I'll show you how to do that and how to get those. All of the notebooks are available on a website called GitHub. I don't know if you guys have ever seen GitHub before. I'm sure some of you have, but I will show you where that's at as well. So you can get all of the data files, all of the material that goes along with it, either from Blackboard or from and the Blackboard has a link right to the course website. So everything is connected through Blackboard. I don't have all of the assignments placed into Blackboard yet. The most important ones that are coming up here are placed there. Honestly, this is the first time I've taught this class. This is also the first time I've taught at Washington University. I've taught undergrad at Maryville University before, but took a break from that for a number of years. So this is, I'll try to stay at least 3 to 4 weeks ahead of you guys as far as putting things out there. So you'll have all of the information there, and I'll be placing the second programming assignment. You can already see the PDF in on the class website. I'll add it to here as well. I also added a discussion area. Okay, nobody's posted anything there yet, but you can definitely use this. I will be checking this, so I will respond to you. You guys can respond to each other as well if you see a question. I am structuring this as a technical class, so there will be programming, so it'll be hands-on. You will learn how to actually do deep learning, and you will learn both what it's for and how to actually create some non-trivial neural networks that will predict a variety of things. So I assume not everybody has necessarily had from experience with the Python programming language. That's the language we will use. That does seem to be the predominant language for deep learning at this point. We'll go through some of the other alternatives that there are, but the original researchers for deep learning, Jeffrey Hinton's group, they created a package called Thano, which is completely in Python. Now, Python isn't fast enough to do deep learning in and of itself. It glues it all together. All of these packages at the low level are C++, but you won't need to deal with that part of it directly.
What Python are we using?
We are using Python 3. So anything 3.4 or higher should work quite well. And I will show you some options too. You can actually use a website that I'll demonstrate here, because Jupyter notebooks are basically completely through the web. So basically desktop applications where you launch something like, I don't know, if I launched iMail or something like that, where it literally is an app running on my computer. Those seem to be becoming more and more rare. What you see a lot of applications do is you start the application and it literally launches a web server right on your computer and then pops a browser open, because JavaScript has become so interactive. So I'll show you a website that is literally running. It's an IBM website that basically you can use free of charge to basically have Python, TensorFlow. We'll be using TensorFlow to do deep learning. That's the Google deep learning package for this. This is all very, very new, state-of-the-art stuff. TensorFlow was not even really available for download even just a year ago. So this is all, deep learning is moving very, very quickly, and there's a lot of new stuff coming out with it all the time. So if you have any questions about these, since I realize people have different levels of experience with Python, I assume everybody's probably done at least one programming language before and that sort of thing. So if that presents a problem, definitely contact me and we can discuss that. But mostly what you're going to be doing is you're going to, I give you a lot of code examples in this on the website, and you will have a code example somewhat similar to most of the programming assignments that are in here. So you'll mostly be taking existing code and adapting it to what it is you want to do. But I'm going to try to take you through all of the major areas of deep learning so that you can see what it's for. Deep learning is, now, have you guys done other machine learning type classification, regression sort of thing? I've seen some of that. Okay. Fundamentally, deep learning is just classification and regression. Again, it does that. We'll have classification neural networks, regression neural networks. But the area where deep learning really shines beyond the other models, like random forests and support vector machines and all of those guys, two areas in particular. One is computer vision. So deep learning has the ability, or certain types of deep neural network have the ability to literally scan as it looks at an image. So it can recognize edges and other things and build this hierarchy of features so that it can recognize things that other models wouldn't really see. In addition to computer vision, now computer vision is really neat and all, but I work for an insurance company, so I don't tend to, they're not all that interested in robotics. However, that being said, there was, you'll hear some more about this too from me, there's a data science competition site called Kaggle, which is very neat. It's kind of like the NFL for the Super Bowl for data scientists. But State Farm Insurance ran a competition where they showed all sorts of images of people inside of cars looking at what they're doing. And basically they would give you discounts if you installed this camera in your car, and basically they saw that you weren't texting and driving or or being a distracted driver. So computer vision does have some place in normal business. But the other area where deep learning is really making some inroads in business, and this is an area that we have some interest in, is time series. So where you have events that occur over time, like the stock market, or in the case of insurance, people going to see the doctor over many years and looking for patterns in that. So anyway, that's an overview of the course. That's the Blackboard website. If you go to the class website, it basically just gives you the course description, which is what we saw there. The objectives for this is just really that you will learn how. Now, deep learning and neural networks are hand in hand. So if you say you're doing deep learning, you're just doing a deep neural network. So they're really very. I mean, there have been academic papers about like deep support vector machines, but by and large, it's neural networks, and that's what will be the focus of this. And also to determine if a deep neural network is really actually a good solution for what you're going to do, because they are a specialized model. Often a different type of model might do something better. There's the old saying, a solution looking for a problem. So you don't want to decide, oh, I'm going to use deep learning. Now let me bend whatever I found into that. And then just there'll be a final project. You can upload it to GitHub if you desire. So then the links I have here, this first link is the course content, which is on GitHub. That's where we'll go to a number of times, and I will explain that. The course syllabus. Programming assignment 1 is up here. I will be adding a link to programming assignment 2. None of these are due for a couple of weeks, so we'll go through programming assignment 1 so that you can just see what that is. And then I put a link here to WashU Blackboard. So this is all on my site at Washington University, so there's a link to it there. If you do a Google search for Jeff Heaton, Washington University, it pretty much takes you right there. So it should be all there. All right, just to introduce myself, my name is Jeff Heaton. My master's degree is from Washington University. I have a Master of Information Management. Got that about 10 years ago. I am nearly complete with a PhD in computer science, and that's hopefully we'll be finishing up sometime this summer. And that's actually remotely through a university in Florida. So I've been working on that for a couple of years since I have a day job that consumes a lot of my time. So my day job, I work as a senior data scientist at Reinsurance Group of America, RGA. They are a company here in St. Louis, in Chesterfield. I do a lot of analytics on various data sources that a life insurance company would be interested in. We're particularly interested right now in underwriting. So how can we look at a wide amount of data on an individual and determine what kind of a risk they are without doing all the very invasive sort of blood draws and urine specimens? I mean, if you're going to buy life insurance, you're going to be poked and prodded, which a lot of people don't like. So if we can get that out of the equation, and younger people, I mean, want to buy the insurance just completely on the phone, get it right away. So we're looking at how can we read all sorts of other data that is non-invasive to get to and determine how we can price the product. All right, so let's... Oh, and also, since this class goes until 8:30, we'll do a break probably right around 7:15 in the middle. So you don't have to worry, I'm not going to go straight through. So that'll be there. So if you click on, so this is GitHub. GitHub is really pretty cool. It is basically a great place to put projects that you work on, that you have, that it's kind of like it's social media for coding. So I have a lot of different things on GitHub. I speak at various presentations, and I put the class material or the examples and other things up there. So if you go to if you click on Jeff Heaton, go to my main site, you'll see all the other various projects that I worked on. This area right here, the class, this is all related just to this class. If you want to just download the entire thing really, really quickly and not have to check it out through Git, you can basically just say download a zip. You click on that green button there and just do download zip. The only thing that I will warn you on that, though, is this is a evolving sort of thing. Like I said, this is the first time I've taught this class, so I don't have all of the material completely posted on here. This will be, I have classes 1 through 4 just about created as far as the code that I want to go through, but it will be added to here, and you can literally see when I've updated some of this. Some of this I was doing pretty good on and working on in the summer, but not all of it. All right, so all of the data files that we will use, I will put in there. And again, if you do the download, that gets you the whole thing. And one thing that Get does is basically you can put something called Markdown. So Markdown is kind of like HTML, only more simple. So you can very quickly create textual information like I have here. So you'll see Markdown intermingled with this. And you'll also see these IPYNB files. Those are IPython notebooks. When you download those, you can basically open them right into IPython and look at them and run them. You could get through this entire class just using IPython notebook if you want to. You can also use a Python IDE like Spider or PyCharm or any number of those. I have some links in the page that'll help you with that. Let's see, and that's all the information that I showed you before. The syllabus, the PDF, has more information. It has all the required sort of information that Washington University wants me to put in there as far as what the grading scale is, what the percentage weights are. The percentage weights are all the same as they are on Blackboard, so I really like Blackboard when I was a master's student, so that's what we will use heavily there because it's great. It gives you everything all in one spot. So this is what we will go through. Next week already we don't have class because of Labor Day. And basically I am not going to do in-class exams, so I'm not going to do like the midterm and the final exam where, I don't know, I get out the stopwatch and you all guys have paper and kind of just go for it. Because everything here is open book, open note, open internet. I definitely don't have to do anything at my job where I just regurgitate it from memory in a small room. So that's what we will do. Now, can everybody see that okay, or is it better with the lights off or on? Is this okay? Okay. So I can see it right here. I'm covered. And then, since we're not having a final exam, I am going to use the final class session as a makeup class, and I do very much apologize for this, but I have to, on 10/24, I have to be out of town actually giving a presentation on stuff very similar to this, so I can't make it that time. So there will be, just so everybody knows ahead of time, on 10/24 there will not be a class session. In return, you don't have to take an in-class final exam, so that might work. Okay, so on this, basically, you can go through everything up here, but the links will be down here. So if you click on one of these files, literally in GitHub, GitHub is pretty smart. in terms of it knows what file types are. So it knows what a PDF is. It knows what an IPython notebook is. So this IPython notebook, it basically opens it and shows you what it actually looks like if you were to open it in Jupyter Notebook. The only thing is when you view them in GitHub, so this is just me on GitHub, it won't actually execute it. So I mean, this is just a static website that you're viewing right now. You can't actually go and make changes to any of the Python code in here. So the way that I recommend running them and the way that I will run them in class, this is great just if you want to go look at something real quick, but the way I will run them in class is I will actually run them in Jupyter Notebook. So that way if I want to make a quick change to something just to demonstrate it, I will have that ability. So I have a link to it. Let's see, I'll just switch over when I get to that. I'll use GitHub for now, and that's probably kind of small. If I ever start going through something that is too small on the screen, stop me too, because the browser just does not seem to remember my zooming. It seems to always just go back whenever I open up something new. But this is basically the course breakdown. The class participation and attendance is 10% of the grade. That is, I really don't have any specific rules for that. That is just you've shown up for, it's probably the easiest 10% you'll get in the class. But if you miss half the semester, I might take it away from you, but that's the idea on that. And I do encourage you to participate in class discussion. I will, anytime you have a question, just stop me and let me know. And I will attempt to foster that as well. There are 4 programming assignments. They're typically have 5 parts to them, so each one has a little section of code that you write. Mostly you can get a lot of the code for the programming assignment literally right from that class's GitHub IPython notebook. So you can't just literally copy and paste it and it's done. That would be no fun at all. So you will make some changes to it, and I'll explain some of that as we go through that. The first program is really just, tonight we're going to do an introduction to Python. So if you're already very familiar with Python, tonight might be a little bit boring. We're going to go through just some of the basics of Python, how to get the iNotebook, the major parts of Python that you'll be interested in for this class. And then just these Python has lots and lots of third-party packages, and that's really its power. There's only a few that we'll use for this class, and I will cover those and give you some links so that you can familiarize yourself with that if you need to. So we'll go through the programming assignment. The first one is really just getting data in and doing some basic processing on it with Python and something called pandas that works with Python. And basically just giving me the results from this. For each of these, what you'll submit to me is just a zip file that has your data output and the IPython notebooks, and you'll just submit that on Blackboard. And I will take a look at them that way. So the first one is really just Python for data science or for AI. TensorFlow, which is the deep learning package that we're using. So this one will get you into some basic classification. I should say classification and regression, because this assignment does cover both. And the first 2 are due before the midterm. The second 2 are due after midterm. So I'll have program 2 posted to the website sometime this week so you can see what it looks like. And then 3 and 4 is where we really get into the things that deep learning is really, really good for. So we'll start with time series, which is the area I'm probably the most excited about with deep learning. We'll learn something called LSTM, which is long short-term memory. That's a very hot topic right now in deep learning. And time series covers a lot of things. Even speech recognition, really, if you think about it, is time series because it's digital signal processing. It's, if you looked at my voice on that little sound recorder, you would basically see it's a bunch of samples over time. The midterm will be done through Blackboard. It's just really some test your understanding sorts of things. I will put it on there, it'll be assigned, and then it'll be due like a few weeks from then. You'll submit it completely through there. It won't be creating a program. It'll be more looking at a Jupyter notebook that I give you, which is a data set that I've created a deep learning analysis from, and I will ask you some questions about it, just to see that you've understood some of the things that we've talked about. And then the final project will basically be a Jupyter notebook type, very similar to what I gave you to analyze for the midterm, except, and you'll get some latitude. If you want to do something with computer vision, you can. If you want to be very brave and do computer vision and or time series, you can. Or if you want to stick to more just the classification and regression, that's fine as well, because that gives you a chance to use it for what you think. Yeah, I mean, it just all depends on what you're interested in. If you want to work for NASA and design the next Mars rover, then maybe the computer vision might or the more realistic one would be to go work for Tesla and work on self-driving cars or something such as that. But the computer vision is pretty interesting, and we will do some examples with that. Now, the course textbook is a book that I am the author of, so if you have any questions about what the book is talking about, hopefully I know. Otherwise, I don't think anybody will. The book is about a year old, so some of the information in the book some of the information in the class is beyond what the book has, because the book's about a year old. TensorFlow didn't exist when I was creating the book. So if you look at the book examples, they make use of something called lasagna, which is based on Thano, which is still a good package for deep learning, but it's just not as good as TensorFlow. TensorFlow, you install pretty much the whole thing, and it's there. Yeah, and that's me. We pretty much covered that. I do have links to my social media. I've already gotten a few LinkedIn requests from you guys. That's perfectly fine. Glad to do that. Some of the course resources. IBM Data Science Workbench. That's really pretty neat. That is basically Jupyter Notebooks, Python, completely in a web application. So I will use that to run most of the applications that I will show you in class as we go through the demonstrations. And this gets you away from having to install everything on your local computer. So if you want to install Python, pandas, all of this stuff on your local computer, you can certainly do that. But if you want to, and there are some issues that go along with installing it on your computer, and I'll get to that in a minute. But if you want to do it completely just in the cloud, so to speak, this is definitely a way to do it, and I will show you exactly how to do it because that's how I will be doing it. Yes. You could do the entire class in IBM Data Science Workbench, and just to make sure that that's true, that is what I'm developing all the class material in. One thing that's neat about it too, because whenever I hear IBM or Microsoft something, I always think, okay, this is their proprietary thing in the cloud, and if I use it and they just go away tomorrow or change it, it won't work anymore. But this is all completely standard Python, so I can literally, and I check that too, just to be sure, I can download the Python. I have to do that because actually the website does not have, the web version does not have a spell checker. And that would be a real problem with me. So I pull them down locally so that I can check them out. And by the way, IPython notebooks, if you view them raw, they're really just JSON. So it's a bunch of JSON code that has all of this in there. So it's all quite open, and then that's GitHub interpreting it. So, okay. Yeah, it's the biggest issue you might run into with running stuff locally is TensorFlow. Python itself works just fine on any platform. TensorFlow also installs quite fine and works great on your computers, so long as they're not something to do with Microsoft. So this is a really interesting aspect of deep learning and the more cutting edge machine learning packages. I don't know how many packages I've gone to literally and wanted to use it in Python, and I raised installation instructions for Mac. Oh, very easy. Installation instructions for Linux. Easy as well. Windows. Yeah, we don't officially support that. There was this graduate student who got it running like 3 years ago. Here's a link to his page. Oh, look, that goes to a 404 because he's graduated and has moved on somewhere else. So Windows is a bit of a second-class citizen in this world. And the reason for that is Windows just does not have a good C++ compiler. It has a somewhat good, expensive Visual Studio C compiler, but basically when you when you use Python and you try to install something, it needs to invoke a C++ compiler to do this, because this stuff is not all written in Python. Python is often referred to as a glue language, because if you try to write everything in Python, it will be slow compared to a language like Java or C++. It's just, and I'll even see people sometimes say, oh, Python's awesome. I wrote something that is way faster than this other program in C++ or Java. Okay, that means you're a horrible C++ or Java programmer if you literally wrote the same thing in both and you could not get the one to go faster in the other. But so there's a lot of misconceptions there. But Python is really pretty fast for the things that you will need to do it. But you would not want to write deep learning all the way down to the activation functions and linear algebra transformations purely in Java. You can do it in Java. There are versions in Python. That would be bad. So that's also the reason there's only a few things that won't work in that in the data scientist workbench, and I will demonstrate those from this computer, but none of them are related to assignments. So all the assignments, everything in the class, you can do completely from there. The only thing I'll show you that doesn't work in there, two things really. One is so basically deep learning, these neural networks, they're all expressed as a compute graph. If you've done Spark, it's pretty similar. You're building this sort of compute graph where it's a directed acyclic graph. And they've somewhat broken the directed acyclic graph. It can actually loop back on itself now in TensorFlow, so they say it's basically a directed acyclic graph with loopbacks. Okay, do they not know what acyclic means? But that's basically the idea there. So there's a neat tool that comes with TensorFlow that lets you basically browse the compute graph. You can't do that in Data Science Workbench, but I'll show you how to do that from the command line. It's very rare that you need to do that unless if you're maybe doing academic research and you want to create your own specific type of deep neural network that is not like the other ones where you want to create your own unique structure, then yeah, you'll probably want to create your own compute graph, but we're not going to do that. And this is more application of off-the-shelf stuff. So what is deep learning? Deep learning, first of all, it means neural networks, at least in the context of this class. There have been applications of deep learning, especially in academia, to things other than neural networks. So if you're in a PhD program and you want to write a dissertation, one of the surest fire ways to do that is find two unrelated sort of technologies and write about something in the convergence of those. If you try to write in mainstream deep learning, you have the risk of basically Jeffrey Hinton and his crew totally changing the definition of what that is, and your dissertation's going that way and the rest of the world goes that way. That's a disaster. You're in school for like 3 more years then. So you don't want to do that. So some people have done that where you'll basically see, oh, deep learning, that's hot. Oh, support vector machines, that's interesting. Let's do a deep support vector machine. So you'll see that kind of thing. Not necessarily mainstream. So deep learning is neural networks. What is machine learning? I've seen this diagram all over the place, and I don't know who to originally attribute it to. It's not my original creation, but traditional software development, basically it's a Turing machine. You have input data, you write the program code to transform that input data how you want it to, and then you produce the output. The computer produces the output, and you check it. You say, okay, based on the program code that I wrote, does that make sense? Machine learning programming, you have your input data, and you have your expected output, so you know what you want the data to look like, and often that works well in business. For me, I have underwriters give me all these cases. Here's what we decided on each one of these. We then write something that produces a model. And when I say model, that means the machine learning algorithm, like a neural network support vector machine. So anyway, you provide it with the input data, the expected output data, and your output is a model, or the case of program code. The LSTMs that we look at, they really are a program. They're Turing complete. And in computer science, when you say something is Turing complete, that means it's a Turing machine. It's a universal computation engine. It could do anything that is computable. So that a standard neural network is not Turing complete. But so you can create programs that learn some really cool sort of things. And the areas of machine learning, so predictive modeling. Now there's different terms for all of this. I will sometimes be asked, what's the difference between data science and machine learning? Or what's the difference between artificial intelligence and machine? Well, it depends on who you ask usually. But for me anyway, AI is the overarching sort of everything. Basically having the computer learn without you programming every single rule into it. Predictive modeling is very much what I do for a living. This is where you have columns of data. That's the Iris data set, a very classic one. And you have some output, and you want the computer to learn how to produce that output, how to find the patterns so that it can do that. There's computer vision, which if you work in the vast majority of the companies that are not on the two coasts, you probably won't do as much computer vision. There's some applications of it, definitely, but that is where you're basically making sense out of these images. This is a really classic data set that I have there. It's really pretty interesting. They have different pictures of airplanes. I think there's like 9 or 12 of those, and basically you're trying to teach the computer to recognize all these different types of like one, they did cats versus dogs, where can you tell the difference between a cat and a dog? And if you look through that data set, there's some interesting things. For the dog, they have one of the images is a little kid with a dog mask on, so that's kind of tricky. And then time series. This is actually sunspots, but any sort of periodic data that occurs over time. So that's very common in business. It's a very real-world application of deep learning. So if you're going to use deep learning in your typical sort of corporate job using data science, and data science is where mainstream businesses really get into artificial intelligence, unless you're working for Google or one of the technology companies. So those are the 3 areas that I'm breaking it up into. There's others, beyond this. There's recommender algorithms like Amazon when you log in and they say, oh, you might want to buy this or that. That's a recommender algorithm. You don't really use deep learning for that, so it's out of the bounds of this course, but there is life beyond classification and regression. Those are the two most common applications of this, and I have them kind of listed there. Regression, that is where all of these are where you have input columns and you want some sort of an outcome. Regression is where you have a numeric output coming from your inputs. One data set that we will use in here that's very common for regression, I try to use standard data sets, particularly from the University of California, Irvine Machine Learning Repository. And I'll show you a link to that, but basically you will choose, for your final project, you will choose a data set from the University of California, Irvine. I mean, they have hundreds of them. Something will be of an interest to you, or you can go to Kaggle to get something. The Kaggle ones are harder, so it's up to you what you want to do. Regression, though, one thing that is interesting about regression, we probably won't do this in this class, but neural networks do support it. It's called multi-regression. So normal regression, basically you have a couple of inputs, and then the neural network or the model gives you some sort of numeric output. It's like your standard equation. Well, most equations, hence equal, return one thing, unless it's maybe a vector. But a neural network, you can have multiple output neurons. Normally, if a neural network has multiple output neurons, it's a classification, but you can truly create a multi-regression neural network where it's regressing on a bunch of different numbers. That's often used in robotics, where you will have the output neurons connected to a bunch of the servo sort of actuators, the things that move the robot. So that's one application of that. We will only use multi-output neural networks for classification. But I'll show you an example of that next time. And then there's classification, which is basically where you are trying to classify something. So that neural network that I showed you earlier with the data sets, or with the images, and there were 8 or 9 classes. Basically, classification is taking the input and trying to put it into one of the classes that you have there. If on those 9 or so different image categories that they had, if you give it an image that does not fit into one of those classes, like I don't think there's a class for spaceship. If you gave it a picture of a spaceship, I don't know, it might think it's a car. It'll put it into one of the class. They don't create new classes. It'll force it into one of the existing classes. Unsupervised, yes, then you don't tend to do unsupervised as much with neural networks. You do semi-supervised. So basically, unsupervised data is like the recommender algorithms. So when you log into Amazon and you basically tell it, it tells you what book you might want to buy, they didn't create a training set for that where they told it what the right answers are. Okay, these kind of people normally buy. There's just too much data. So unsupervised learning is typically clustering. So you will take all of these data rows, and what it would do, and we will see an example of that. We'll see a very new and interesting clustering algorithm called TSNE. But it would basically take all those images and cluster them, and you would tend to notice that certain, maybe there would be a new cluster that you had not thought of before. So one thing that's very interesting is when you cluster unsupervised, like the digits, the handwritten digits, there's a classic data set for that we will see. You'll notice that the 7s it's sort of a oblong area with 2 clusters. Well, one is the European 7s with the hash through it, and the other are the American 7s, and then you see the 1s come in very close to the 7s, because if you have bad handwriting like me, 7s and 1s look really pretty similar. So that's kind of how that works. And then semi-supervised, you don't hear about that quite as much, but that's where you have partial labels. So maybe, and we have that some in our data sets in insurance. So maybe the underwriters will give me a bunch of cases where they have underwritten them and they know what the outcome is. That's supervised. But then a lot of them, we have the data, we just don't know what the outcome is. And what you will usually do, there's a bunch of ways to support it, but you basically train the neural network on where you'd have the labels, and then have the neural network produce outcomes for the unlabeled data, and then you retrain on that whole thing. And those cases where you didn't have the labels, even though you don't know if the label is right because the neural network gave it, that gives it. And then another common thing for semi-supervised is you use the unlabeled data to initialize the weights. So we'll see examples of that as we go through. So what are neural networks? Neural networks are one of the original model types. So neural networks have been discredited at least twice, pretty much thrown on the dustbin of AI, because there's 4 individuals who have just doggedly looked at this area of research and not really given up on that. There's a pretty good article that I have linked there called "The True Believers," referencing to the first deep neural network ever. It was there's been a type of neural network for a long time called a belief neural network. They were able to get it adapted to work for deep, so it was the deep belief neural network. And we'll see a little about those as well. Deep belief neural networks are not used quite as much anymore. We've got other ways of doing that. But the people, Jan LeCun, who basically, he's the computer vision guy. So he's basically created the convolutional neural network, which is what we'll see for computer vision. Geoffrey Hinton, pretty much the father of deep learning. He has also done a lot with Yoshua Bengio. It's a French name, which I'm probably pronouncing incorrectly. And of course, Andrew Ng, who works for Baidu now, and these guys all started at university. The only person who has not left academia to get the gigantic paycheck from a tech company is Yoshua Bengio. So that's they've all basically gone to, I believe, Jan LeCun works for Facebook, Google, academia still, and Baidu, and if I'm saying that right. So that's basically where they have all gone to, and I have links on all of them. So on my dissertation, I have probably about 6 or 7. I have about probably 15 to Geoffrey Hinton, and then 6 or 7 to each of those guys. So they've written a lot of seminal sort of papers in this area. This class is very much on the application of deep learning, so I'm not going to really go into I'm not going to have you read like academic papers from the underpinnings of this. If you want to know or need to know where any of this stuff originated from, I can certainly point you in the right direction. So why deep learning? Basically, there's a lot of different model types out there. There's support vector machines, there's random forest, there's gradient boosting machines. By the way, one that is just coming on with a vengeance right now is the gradient boosting machine. I've been to several conferences, both academia and industry, where I have heard it said several times, if you learn just one machine learning model, learn that one. It does classification, it does regression. It also works really well with deep neural networks. So later in the class, I will show you how to ensemble, which is where you combine more than one model together. That's a very powerful concept. All the winning Kaggle competitions are ensembled. So that's very much the state of the art. Random. Now, both of these two are ensembled models, meaning like a random forest, it's just a whole bunch of trees. Basically, you create one tree, you look at your data set and you realize, oh, where did the tree do good? Where did the tree do bad? Oh, it did bad there. Let's train another tree on that part. So you keep adding tree for the training on the residuals, the places where your first tree did bad, and you build it out to this entire forest, and then they vote on what the output is going to be. Gradient boosted machines just took that one step further and used gradients, derivatives, to do that more efficiently. So why using deep learning? This is a diagram that I saw from Andrew Ng in one of his presentations. This is a completely non-empirical, meaning it comes from no real data. He just drew it according to some of his own observations. Basically, what this is saying, and I observe this all the time, I don't really observe that as much. I think that's a little bit of, you've seen the Gardner hype cycle, but that's a little bit of irrational exuberance. But basically what it means is, say we've got, so this is the amount of data you have, and this is the performance, how good your model is performing. So I tell my boss this all the time, oh, if we could just have more data. The problem is with these older algorithms is they tend to go asymptotical as you add more and more data. So if you just have a little bit of data, your performance is not going to be that good. You add more data, performance gets better and better, and then you start to reach this point of diminishing return, and the algorithm just sort of bottoms out. So the thing that I don't like about this almost linear expansion into awesome performance is this tells me almost that literally if I just had enough underwriting cases, I could write something that was perfect almost. So, but this is somewhat true because as you add more and more and more data, the older algorithms do tend to break down, and this is an area where deep learning can excel beyond just the computer vision and the time series that it's mainly used for. So there's a lot of excitement with this in terms of getting deep learning working on Spark so that you can have both a vertical, like TensorFlow supports both vertical and horizontal scalability. We won't get into that. The vertical is basically you just get as bad of a machine, good of a machine, powerful of a machine as possible. You'll see machines with like 4 GPUs on them and a bunch of memory, so that's vertical. You can only go so vertical. You can only put so many GPUs or memory or whatever on a single box, and it's extremely powerful, but ultimately you need grids of those machines. So like Thano, which is Jeffrey Hinton's group's answer to deep learning, is very much vertical. You can put GPUs on it, you can do all this kind of thing, but it's not horizontal. So the two newest ones, CNTK, which is Windows, and TensorFlow, which is everything but Windows. Microsoft makes CNTK, by the way. They are the two sort of leading ones showing that basically big companies are getting into this. And by the way, GPUs, I said there were 2 things that you could not do in Data Scientist Workbench. GPUs is one of them, mainly because they're expensive, and IBM's not going to let you use them for free. So even the image neural networks that we'll do in here are not of the size that you're truly in the GPU category where you have to have that. GPUs are very much, they've been in and out of popular use in computing other than video games. I mean, that's what they were created for. But they're very much a one-trick pony in the sense that they don't do a lot of things very well. But there's 2 things that they do really, really well: video games and deep learning. So the the mathematics of deep learning and the mathematics of a video game are very similar enough that even gamer GPUs, so just a GeForce Titan, which is I think one of the highest end ones, I mean, maybe a $600-700 video card will really speed up a deep neural network. They have higher end GPUs that are made specifically for this kind of thing. They're not gamer type devices. You can play a game on it, I guess. I don't think the performance would be all that good, but they're made for these kind of applications. But the cloud is great for that. So I will show you how we can basically request a GPU instance from Amazon. And they're really not even that expensive because I can run it for just the 10 minutes or so that we'll actually use it and show you how it does in 10 minutes what this machine would probably do in about 15 hours. So it's a pretty good performance ratio. And then the two areas that so other than throwing massive amounts of data at it, the other area is the convolutional neural networks for computer vision, and the recurrent neural networks, which are basically neural networks with recurrent connections, and those allow them to deal with time series. And the only difference between a recurrent neural network and a normal neural network is when you give a normal model, like a support vector machine or a random forest, you give it some set of inputs. It's always going to produce the same output, unless you retrain it. So you give it these, if you do the iris data set, and you give it these 4 measurements, and it says it's this kind of flower, it doesn't care what flower it saw before, it just cares the one flower that you are giving it. Recurrent neural networks don't do that. So those inputs that you give it, it's finding patterns over the combination of patterns you give it. So if you're doing the iris data set, don't do a recurrent neural network because you're going to get weird results because you don't care what came in before. But if you're putting a bunch of stock prices in, if you know company A traded at $65 today, what it traded at the last few days is important because that'll show you some sort of a trend. So, and then Python for deep learning, there's several options for this. Thano, which is kind of the original one, University of Montreal. TensorFlow, which is from Google, that's currently my favorite. And CNTK from Microsoft, which I think is also, it's actually a little faster than TensorFlow in its current version. Okay, so the software installation on this stuff. So like I said, this is a technical class. There will be some programming with this. You can use the IBM Data Science Workbench. The link to it is here. That's its logo. By the way, I do believe, I'm teaching this class again next semester. It would not surprise me if I thought at the beginning of the summer that Google would have this solved maybe by the time, and I could say, okay, to do Windows, do this. But no, they haven't quite gotten to it yet. The best way, if you truly do want to run TensorFlow on Windows, is there's something called Docker, and you can get a Docker image and run it in a virtual machine. So that is literally the only way that they let you do this in Windows for them yet. So this is sort of the screenshot to this, and we'll go into there literally like right after the break, which is coming up here in about 10 minutes. You can go into here, you can click on Jupyter Notebook or My Data. Those are really the only two links you will use in the Data Science Workbench. The Jupyter Notebook that it launches is exactly the same Jupyter Notebook that you would have if you run it from the command line on Mac, Windows, or any of those. and you will, when you basically launch it, so if you do want to use the data science workbench, you have to log in and sign up for an account and do that sort of thing. I'm really surprised that they offer, I mean, they're basically giving you a free 4-core, about 8 gigabyte RAM virtual machine. Okay, so I'll show you this in a moment because that's what we'll be doing. If you want to install it on your computer, and I'm not discouraging you from doing that. If you have a Mac, it's actually pretty easy. If you have a if you have a Linux machine, it's also relatively easy. If you have a virtual machine running Linux in a Windows computer, it's also relatively easy, just slow. So that's basically the way that works. And if anybody is particularly interested in running it in Windows, I could give you a virtual machine that I've installed of basically everything ready to go in CentOS, which is, I'm sorry, not CentOS, Ubuntu. That's the one that it supports the most easy. That's another thing that's nice about Linux is if I want to give you guys, say, a virtual machine of something, I can just give you a Linux virtual machine and then I don't have to worry about breaking copyright law, whereas if I gave you a nice Windows 10 installation, then I guess that would be okay so long as I gave it to you without the license key and you went and paid a couple $100 to buy it. Who wants to do that? So one thing that's Python is almost 2 programming languages. This is probably my chief annoyance with Python. There's Python 2. When they upgraded to Python 3, they made a lot of breaking changes. Breaking changes are when you change something and you break existing code that's dependent on it. You make too many breaking changes and your user base forks, meaning half of them stay with the old and the other half go with the new. So both Python 2 and Python 3 are being supported essentially independently by the same people. So you will see Python 2 very much alive and well. As much as possible, I try to write my own Python code so that it works in both. Sometimes you can't help it, and you have to write something in Python 3 that'll break 2. But all the code in this class is assumed to run on Python 3. I have not tested it all on Python 2. I would bet it's about 95% compatible. I'm sure that so I will probably at some point go back and try to, if there's any easy things to fix between the two. The biggest change is actually Unicode. So in Python 3, it has really, really good support of international character sets. That's a very important feature for me at RGA because we deal internationally with all sorts of companies. In an ideal world, all of these companies would give me UTF-8 Unicode characters. In the real world, that's rarely the case. I have certain companies from Korea that will give me Korean data sets in Little Indian when I would have expected Big Indian, other sorts of things. And Indian in that case is ENDIAN, meaning is the big part of the byte at the end or the beginning, or is the most significant byte in the beginning, that's Big Indian, or at the end, Little Indian. So quite often. So we end up using Python to get them in and then convert them into Unicode, and then Excel's happy to read them. So I'll show you some more about just what to install and what we're using in Python, but we're about halfway through, so we'll go ahead and take a 10-minute break. We'll usually have one of these right about in the middle, and then we'll start up, I guess, about 7:23 or so. All right. Okay, so if you are going to install it on your computer, Python is kind of like Linux in the fact that you don't just install Linux on your computer, you install Red Hat or Cent or one of those. You can't install pure Python. And if you just go to python.org, you'll get that. However, to install pure Python, especially on Windows, again, that's sort of the third-class citizen in the Python world, you have to install these binary packages because it can't just go out to a C compiler like in Mac. So I very much recommend a package of Python called Anaconda. And they have a version of Anaconda for Windows, Mac, and Linux, and it works very well on each of those. So the Anaconda people, they're a startup company. We've actually worked with them a little bit. They do consulting. They're a pretty neat company, really. Basically, they have gone through all of the trouble of getting these binary packages that you need. Is in Python, you need NumPy, which is numeric Python, SciPy, which is scientific Python, all these packages. It's all completely installed with Anaconda. So you would have to basically go and find these binary packages or get the C compiler sort of installed in Python. I've honestly not gone down that road yet in Windows. I forget which university has them, but they do have the binary packages for most of these. Or just install Anaconda and things are somewhat easier in that regard. So if you have Python installed, you can just do -V, and it'll show you the version. So there is a Python 3.5. I'm slightly out of date on this computer, but it basically has it there. You can have multiple copies of Python on your computer, like source activate. So basically, if I do that command, source activate TensorFlow, that basically is an Anaconda command, and I have a link to on my website. I have an article on the care and feeding of a Python environment, how to keep everything up to date, and how to use this. So I've created a special environment in Anaconda where I have all the TensorFlow stuff installed, just to keep it segregated, so that I don't accidentally damage it doing something else. So if I do Python -V now, you'll notice that I do have the very current 3.5.2, and I have TensorFlow installed there. So basically, that is the how you can kind of use that from the command line. You get a command called conda install. So basically this installs a lot of packages for you. If you want to install Jupyter, you just do conda install Jupyter like that. Of course, you have to spell Jupyter wrong, I mean correct, to do that. So they do spell Jupyter, Jupyter. And then once you have that all installed, you can do Jupyter note. I'm just following my command right there, notebook. And basically, it starts up all that, and then it launches essentially a web browser here. And this is really exactly what the data scientist workbench from IBM gives you, except this is literally running on my computer. So I might use this when I give you an example of something that's more heavy-duty multi-core, because this is a quad-core computer, so it has eight virtual cores by virtue of hyperthreading. So it's quite a bit faster than the IBM one, but just to show you how to use, and then this keeps on going. This is basically your web server running there. I'm going to Control-C it so that it's not there, and it gave you the web address if you wanted to access it directly. So if you use Data Scientist Workbench, so you just go to there, and basically, first time you would click Sign Up, and it will take you through the whole sign up process. I think whoever created this really likes dogs because there's all kinds of dog applications in this. So when it's updating, you'll see this dog chasing his tail, and he'll say, I can do this for half an hour. You might want to come back later. And they're not kidding. It will do it for half an hour, and it'll continue doing it while you're gone. So you'll see me always just click login, and I was already logged in. So it takes you to here. And literally, this is a web front end to a virtual machine. So if you go to my data, yours will be much more empty than mine. But these are all the my data. So these are all of my files, which I think I have it zoomed in to the point that you can't see the file names, which is pretty useless. So these are all various files that I have here uploaded to my data directory. So if you generate something, so like when you run the homework assignment, you'll generate submit files, and basically you can download those from there, and that is one of the files that is the submission to the homework assignment. So it downloads it. It's an Excel file. No, I don't want to do an upgrade now. So these are all just CSV files. So this is one of the files that you will generate for the first programming assignment. So you would find all your files on that folder, which is my files. And where you'll spend most of your time is the Jupyter Notebook, which is here. And these are all of your notebooks that you have over here. So as you can see, I have quite a few of them loaded into here. If you download the zip file from the class, your area will be empty over here. You can basically just take a IPYNB file and just drag it into here, and it uploads it and opens it for you. You don't want to keep redragging it because you'll be re-uploading it over top of itself. But once you have these files here, like this is the class 1 introductory side. So this is actually literally running in a notebook. So that's just what we looked at before. So I could make changes to it. And if you wanted to change something, you just double click. And this is just Markdown. So that's how I create the text that goes along with it. These are just hyperlinks. You click the little run, and it runs it, and it turns it right back into that. If you want to create a new notebook, you click that, and you pick the language. So you would pick Python 3. And then it creates a brand new notebook for you, and you can write anything you want to. So just a loop from 1 to 10, you run it, 0 to 9. So there's some programming languages are 0-based. Python is 0-based. It's not 1-based. I've heard it said in real programming language, number 1 is second best. So it's 0 comes first. So that is that. And that's how you would get into that. I'm really trying to keep the amount of packages that we deal with in Python relatively small so that I'm not overloading you with every package that known to man in Python. The main ones that we will deal with are really these first ones listed here. So scikit-learn, you may have heard of scikit-learn. It's had quite a bit of traction. It's a way, it gives us a lot of machine learning capabilities in Python, and I will show you how to use that. Pandas is pretty much our data frames for Python. So anything that you do with pandas get you very used to working with R data frames. So it's pretty nice in that regard. It's very popular in Python for data processing. Jupyter Notebooks, you will deal with those. The PyCharm IDE, that's an IDE that I use on occasion. There's also the Spider IDE. There's a whole bunch of IDEs for Python. You can choose, or you can use pure Jupyter Notebooks. CX Oracle, that's very important if you want to deal with Oracle. In this class you won't, so I just list it there. If you do have need of Oracle processing, it's very good and very fast. Matplotlib, we won't use a whole lot. I will give you several pre-made functions that use Matplotlib. So this gives you graphics so you can look at different representations of your data. And then the Jupyter Notebooks, they support quite a few things, even LaTeX, which is really nice. That's a way of, you can put very rich mathematical formulas in there. That's just a simple finite difference that I put in there just to example it. And then as far as Python versions, I just saw a typo. If you see xrange instead of range, I mean, that's a real telltale sign that you are in Python. Oh no, that's actually not a typo, that's correct. So if you see xrange instead of range, that's Python 2. That's one of the most common things you'll see because xrange would give you an error in Python 3. If you see print x instead, this is the most common one, and this annoys the heck out of people because the first program that you see in most intro to Python is print hello world. Well, if it's Python 2, it's print without parentheses hello world. If it's Python 3, that would give an error. Because in Python 3, like most languages, all functions have to have the parentheses around them. It works either way, so if you do put the parentheses around it, that will compile and run in Python 2 just fine. But it's just from the old Python 2 days, there's lots of examples that do prints that way. I mean, one of the early versions of TensorFlow, Google did Python 2, and it worked perfectly in Python 3. It's just they didn't put their parentheses around the prints. So they really annoyed a lot of their users who sent them GitHub requests saying, fix that. So if you want to know what version of Python you have or what version of TensorFlow and pandas and all of that, this is a little bit of code. So basically, this code here, you can run it, and it reruns it, and it generates the output. So if you notice, it took it a little bit there. I think it was starting my kernel back up. But it will show you that, okay, this is Python 3.4. This is no longer on my local machine. This is on IBM Data Science Workbench, because I'm running it there. They also tell you the version of the GNU C compiler that you're running. And then the version of TensorFlow. There is a 0.9 of TensorFlow, but it's very new. It came out, I think, just in July. So 0.8 is what we use here. There really shouldn't be any compatibility issues there. There is one thing that they changed, and it causes you to get warnings. So I'll mention that when we get to that next class. Don't really worry about the version of pandas. We're using all very generic pandas that has been in pandas for years, so that's perfectly fine. Same thing for the version of scikit-learn. You shouldn't run into any problems there. And again, these are the big four, so to speak, of software we'll use in this class. Scikit-learn, extremely current, extremely relevant in machine learning in Python. That's sort of it was started as a Google Summer of Code project and sort of took on a life of its own. It's really cool in the fact that it automatically transforms data, and we'll see other things about it. So let me just go through a little bit of some of the basics of Python if you have not seen it before in a programming language. And then, so the rest of this class is somewhat introduction to Python, at least as much as you can do in about 45 minutes. And just to give you some starting points, if you have any questions about Python or you just run into an issue with getting something up and running, or post a message in the website, send me an email. You have my email address. I definitely expect a couple of questions on this sort of thing. This is the one that we did basically already, except before I did just 10, but here I specify the starting point. So for x in range 1 to 10, colon. This is another thing that annoys people who came up from a C++ background, including myself. White space, very important in Python. White space is not white space, it is how you define blocks. So for x in range 1 to 10, colon, so that colon means that's kind of almost like an open curly brace, that means it's starting. If I were to back that print back to here, it wouldn't run because that loop would not have anything indented under it. So those indentations, basically, that's how you're defining your blocks of code. They do. And even the data scientist workbench very much does that. This is another, I tried to give you just some quick example. Rather than giving you a gigantic tutorial to go through on Python, I wanted to give you just code snippets for what I'm going to have you do. So really, for the programming assignment, if you look at the Class 1 and Class 2 and Class 3, which I will be putting up soon, really the first programming assignment, everything is in Class 1. So it's not due for a couple of weeks. So if you have any questions for me, so if you want, we don't have class next week, so if you want to try to get some of this stuff up and running and then have any questions for me next time, that will work. But you also have my email, my phone number, that stuff too. So email will be the best way to reach me, but I am very open to answering any questions you have on these. So one thing that you need to do a lot is we're looping. Sum plus equals, well, that works very much just like many other programming languages. We're adding x to the sum, and then very often you want to print out a number or something. Those braces in there are basically where you're going to insert that number. So this string with these two fill in the blanks, dot format, x comma sum, that is basically going to print out adding 1, adding 2, adding 3, and then the sum so far. So always make sure that the number of fill in the blanks equals the number of things that you provided it, or things won't work. This actually gets really complicated. You can do all kinds of things between those braces with formatting characters. It's sometimes been called a language in a language, but for the homework assignments and whatnot, you really do not need to put anything between the curly braces. Just don't worry about rounding. You can just print the numbers out to as far as they go. That's perfectly fine. So we loop, we do all of that, and then I go back to the far left, and final sum colon, and print that out. So string.format, very useful. That's how you print out numbers. Also too, I always use tabs. You can use tabs or you can use spaces. Using both is a surefire way to get a really hard to debug problem where you are just not sure why Python's dropping out of your loop when you don't intend for it to. This is a very important concept in Python. There's lists and sets and dictionaries. So most programming languages have these. A list is just an array, a set of things. So lists are always square braces in Python, And by the way, single quote versus double quote, exactly the same thing. There's no difference. So I will tend to use double quote on like human readable strings that I'm printing out, and single quote on like constants, but it's a style thing. So I created that list. If I print out C, then it prints out the entire list just in that form, and that's very handy. That's a way to sometimes just print out a list. I also can iterate over it. So for every S in C, so that gets executed 4 times because it's 4 of those in there. So you'll tend to do stuff like that. That can be very useful. And this is also very useful. I haven't seen this in other languages, but I've done the same sort of thing. Often you're going to, for each, you're going to iterate over a list, but you want to know what index you're on. So often in languages that don't have this, like Java, I'll do I equals 0 and then just do I plus plus in here. But in Python, you can literally do for IC in that same list that we had, enumerate. So that enumerate means that you're getting 2 values back on each one. So you get the index where you're currently at and the character. So that can be handy. And that's uniquely Python. I have not seen that in other languages. I'm sure some have it somewhere. There's a lot of languages. You can also create an empty list and add to it. So that creates the same sort of list. You just built it manually. And notice I put C in twice. That's fine in a list. You can have as much duplication as you want. Not in a set, though. A set will eliminate duplicates, which sometimes is good. So see here, I do exactly the same thing with a set. And I just do that. So sometimes, I don't know, if in SQL you do a select distinct, this is kind of like that. If you wanted to know, I mean, I will use this in data sets where I just want to know how many zip codes, unique zip codes we have in a particular data set. So that's an easy way to do that. And you can insert at a position, so that would insert it at the beginning. You can remove. You can also remove at an index. This removes by name. That removes by index. So you can change these lists very much just right in the middle of this. So in some languages, this is not to be done. Like in R, you don't want to build an empty list and just add to it because each one of those lists is being rebuilt and it's bad and performance bad. These are very useful. You will see maps, dictionaries, hash tables. They all mean the same thing. It's just like a dictionary. So we have an entry called name. Name is Jeff. My address, at least in this example, is 123 Main. So this is just a hash map that basically has name and address. Hash maps in Python are extremely fast. So if I have literally created hash maps where I have every zip code in the United States, and each of those is pointing to some value that I need to look up for that zip code. And I can just tear through the list and access those because it's using, I mean, it's kind of a computer science term, but hash maps, it's sort of a way of very quickly going to a particular value based on a key. And hash maps, you can't have more than one of the same thing. So if I tried to add another name into there, it'll overwrite the previous one. So if I print the map, it prints it out in exactly the same form. And then, and this is a very common sort of naming convention for these. You'll see this in JSON, you'll see this in JavaScript, but this is a very common way of naming, of initializing a map. You can also print out just the values. So if you print out just the values, it will say basically address and name. So just the, or just the names, so the name and the address. And you can also print out just the keys. So you have those. Except I have this mislaid. I have that backwards. Keys. See, this is why I will upload that to GitHub. Values. So this is why I like notepads, because you can literally change it right here and then rerun it. And now it's correct. So you can literally make changes right there and see how this stuff changes. You see this a lot in Python, and this matches very closely to JSON files if you've ever dealt with those. So basically, I have a list of dictionaries. So the list is almost like a table. The individual dictionaries are name-value pairs, so like the individual records. And then as far as pets, this is actually true. My wife and I have two cockatiels named Winton and Cricket. But basically, we have a list in here. So this is a list on the outside. Curly brace means now a dictionary or a hash. Name is Jeff and Tracy. Pets, and then I put a list literally right into there. And you can go very, very deep on these. You can then put a map inside of a list and put a list inside of that and a couple of hashes in there, and you can create this whole very XML-like. You can this is essentially XML, is really what this is representing. We won't do a lot of this in the class because we're not going to create these kind of complex data structures. There's really not a need to for deep learning, but you can then print them out, and it maintains the whole thing, and you can use all of the for eaches and that to iterate through there. So just some of the things that Python is. This is one thing that Python, I mean, if you in Java wanted to declare a list, like an array list, and then put a hash map inside of it, you can't just declare it all in one statement like that. You would need code where you created your new hash map, and then you would create a new array list, and you would add the array list, you would put the array list into at the right key. So this is a way that you can define these complex structures of hash maps and lists just implicitly right there. And some of this, when you see it for the first time, when you go back through and look at it, it'll make more sense. If it doesn't, then ask me. Or Google. Stack Overflow works well. But yeah, I'm just giving you lists of. I'm trying to highlight the parts of Python that we'll use the most. Pandas we will use a decent amount. Pandas is really pretty cool. You import pandas as PD, and then anything PD dot is basically pandas. So all I'm doing here is saying that that's where my path is, and I'm saying the file name that I'm going to read to. It basically combines path to the auto MPG. This is a data set. The only reason I'm doing this makes it platform independent. Because basically, if I were to just add this, it might get confused between backslash, // all those different ways that Windows and Mac and Linux do that. So this is basically just saying whatever the path was, concatenate that onto the end of it and form a complete path. So dot is the current directory. In my data directory, I'm opening the auto mpg.csv. If you download the file from GitHub, you have auto mpg.csv. That's a file that I create. I got it from UCI, and then I added headers onto the top of it just to make it easy. Most of the UCI datasets don't have headers. So if you grab them from my GitHub location, you'll have headers. So this is actually pretty simple. You do df, data frame, That's just a variable name, equals read CSV, and I read that CSV, and all this 0:5 means is the first 5 records. So I'm going to print out the first 5 records of that, which is miles per gallon, cylinders, displacement, horsepower, weight. So this is information on cars, particularly cars from the 1970s, which is when this data set was generated, but it's a very popular data set for regression. And the number of cars that have 8 cylinders also gives you an idea of the era that the data set is from. But basically, you can use this data to let the computer learn to predict the miles per gallon for a car with new, where you gave it the weight and acceleration. And also, too, it's wrapping around because there were more columns than I had room for. Origins just says where the car is from, and then the actual name. The name is not too useful for machine learning. So that's just a very basic from pandas. You just read it in and print it out. You can also perform some very basic statistics using, this is all the same thing. I did add this. This is handy, and you'll see most of the examples in this class will have that. That just says missing values. So if some of these data sets will have NA or question mark for missing values, that's just telling it that. And that way it will read those in as NAs. And we'll learn how to deal with missing values. This is just a very quick way to grab only the integers and floats, so that gets rid of the name column. It's just a handy way to strip off the non-numerics. That's how you can get all the header columns, so the column names. Very relatively simple way to do that. And all I'm doing here is basically I'm making it so that I don't have to hard code this to the columns, so it would work for anything. So I get the headers, and I just loop over it, and I'm printing the name of the field, and then I'm basically using pandas to say the data frame for that field, give me the mean, give me the variance, and give me the standard deviation. So it just shows you basically how to calculate that. So the standard deviation for MPG, it puts them in the wrong order a little bit, but the miles per gallon, the standard deviation is that. The mean, 23 seems reasonable for even in the 70s for a miles per gallon. So this just shows you some basic sort of pandas type coding, how you can do these sorts of things. This is also very useful. You will sometimes want to sort and shuffle data frames. So it's always important to shuffle them, because usually when you get data, the order does actually mean something. So like the iris data set, when you get it, it's actually sorted by species. So if you try to break it up and say, oh, I'm going to do the first 20% as my validation set, well, that'll be all the same species if you don't shuffle it. So that would not work well. So all I do here is basically I read it just like before. That line there, if you uncomment it, you will always get you'll use a seed, a random seed, and you'll always get the same, you'll get consistent random numbers. So you'll always get the same shuffle. And that's very useful. Usually I use a seed. Because as soon as I don't use a seed, I will generate a shuffled data set, and somebody on the team will come to me the next day and say, oh, could you give me that same shuffled data set, but with this additional field added? Okay, that was a random shuffle. It will never happen again. It is a snowflake. So usually you will do this. And in Python, you always see them use the random seed of 42. Does anybody know what's special about that number? Yes, Hitchhiker's Guide to the Galaxy. It is the answer to everything, or to the ultimate question that they forgot what it was. So, yeah, so that's You see lots of references to British comedy in Python. Also with the, hence the name Python, Monty Python. That's literally what it comes from. So anyway, but this basically, I shuffled it. You don't really need to remember exactly what these lines do. I just copy them and reuse them. But what they basically are doing is we're creating a permutation and then we're resetting the index. If we didn't do the reset index, these index columns would be all in a jumbled list, and that would let you know what the original position of it was. And maybe you want to do that. Usually I don't. Usually I just want it shuffled and I want to move on. But this is showing the data set literally shuffled, and it doesn't print out the whole thing. And then this is, oh wait, that was actually, yeah. And then this one is showing sorted. So we sorted by name. So if you look at that, you'll see the AMCs are all at the top. And for the first assignment, that's what you do, some basic sorting, shuffling, that sort of thing with the and then saving a data frame. This is how you'll do the code, the submission of the CSV file. So you'll create this new sorted data frame, whatever you do with it, and you basically can do to CSV, and that will write it. Usually I do index equals false. Otherwise, it literally gives you row numbers, which I tend to find annoying because I don't need to know 0, 1, 2, 3 at the far left. So I always do that. So this program, oh, go ahead. Yes. Yeah, and that comes from R, because if you save data frames in R, then you will, you'll get that index column. Yeah, you can get a row ID in various flavors of SQL. And I do print out the word done just because this program would have no output otherwise. It outputs to a file. This is very similar to something that you do in the first programming assignment. So basically I'm showing you how to create a calculated field. So we basically want to convert the kilograms to pounds. So we're just adding a calculated field. So we're adding a new field called weight kilograms, and it's basically the weight times that, which converts it. And then I do a very simple round. Otherwise, you would have all kinds of decimal places on there. I just convert it to an integer because all of the weights in pounds that they had there didn't have decimal places. So I just decided to go ahead and convert them to int. So that's my new calculated field that I had added. And it's basically just doing a data frame insert. So when you see the programming assignment, there literally you can find most of the syntax type of things that I want you to, most of the functions and pandas that you need to do in the class assignments. I'm just trying to keep you from having to scour the entire internet looking for these kind of things. You may need to scour the internet a little bit looking to see exactly how they work in your particular case. But, good question. Notice how when I printed it before, they were somewhat hard to read. If I just, it's basically a print, but it's telling Jupyter to put a nice table around it for you. So if I change this to just print df, and I ran it, then you have that, like we had before. But if you do this, it formats it a little more pretty for you, and you can actually scroll to the left and to the right. Basically, in statistics, you don't really need to deal with the equation to this much. I'm giving it to you just if you want to see it. But in statistics, there's something called a z-score, and we'll do z-score transformations. Basically, you're just turning a number into the number, and I've got a description there and some links for you. If you haven't seen z-scores before, basically if you have a z-score of 0, that means you're right at the average, right at the mean. A z-score of 1 means you're 1 standard deviation above whatever the mean was. A z-score of -1 means you're 1 standard deviation below. And neural networks really like z-scores. If you z-score the inputs going into them, they'll often predict better. Other model types, it doesn't really matter that much. But neural networks particularly like their data centered around 0. We'll see more about z-scores in the next class session. But this is just showing you that basically pandas can calculate the z-scores for you. So basically what I did is I took the miles per gallon and I created an additional field, a calculated field called also called miles per gallon, so it replaces miles per gallon, and you'll see that miles per gallon no longer looks nice like we had before, but that means this car has a below average miles per gallon. This car also does. And if you see positive values, then you know it's above, so that's above average miles per gallon. So that's just showing you how to do sort of a z-score transformation on that. Missing values. Often your data sets will have missing values. So the miles per gallon database does have a missing value in the horsepower category. So what a very common technique that you do to get rid of those, and you'll see in other machine learning classes, is we take the median of it. So we calculate the median of horsepower. And basically, you just do this command. There is fill NA, so we're taking the horsepower column, we're filling the NAs with the median that we got here, and just assigning it back into there. So this is a very handy command that you can use when you're encoding data for neural networks. We'll get a lot more into this than the next class. You'll see better examples of this, but this is basically how you eliminate NA values, because if you just pass the NAs straight into the neural network, you'll get an error because it doesn't know how to deal with those. So it's almost like saying, we don't know what the horsepower of this car is, so we'll just put the average, or the median in. So so that one I didn't add in. You would want to do one or the other. You can simply say, I'm going to just drop all the rows that have NAs. Generally, that's not recommended because often the NA values, there's reasons that they were not NA. So, and then another, we'll see examples later, but you can get more advanced with filling in the NAs, because say you had BMI, body mass index, and you had males and females. Well, the average, the median BMI is very different between males and females. You have what you call bimodal data. So the nice standard distribution that you have has 2 humps. And in biological data, usually when you see 2 bumps, bimodal data, that usually means you've got males and females mixed together, because a lot of the values are different between the two. So you see that a lot in underwriting data. And then concatenating rows and columns. So sometimes you have multiple rows, you just want to concatenate them, or multiple columns, you want to concatenate them. I show you basically how to do that. So here I create an entirely new data frame. So I load the data frame just like before. I extract the column of horsepower. I extract the column name, and then I basically use concat, and I create a list here. And you have to do the axis 1. That tells it that you're concatenating columns. And I create an entirely new data frame that has just those 2 columns. It's like a view in SQL, sort of. So that can be handy too. It's just, I'm kind of quickly going through these, just giving you sort of a recipe book of things to look at that will be, so I create these notebooks for each of the classes. I mean, I'm definitely not trying to teach you every detail of Python and pandas in 2 hours, but I'm giving you starting points to look at that and use your experience from other languages to kind of put that together. If you want to concatenate rows, so if you basically did exactly the same thing, but notice I did not put the axis on there. Now it's not concatenating columns, it's concatenating rows. And this gives you not at all what you would probably want. You're going to have all the names of the cars at the front and then all of the horsepowers at the end. So instead of putting them nice side by side, it put them like that. Sometimes you might want to do that, but in this case you probably did not. And the only thing that was different is the concat, I didn't put the axis in. Axis equals 1 basically concatenates columns, axis equals 0 concatenates rows. So that part is... And then we will definitely get more into this when we go through TensorFlow, but training and validation. I put this in here because one of the questions in question 1, or in the first assignment, does ask about this, but I just give you a review of sort of training and validation data and k-fold. So basically, if you have your data set, you might take 80% of it for training, 20% of it for validation. So you fit the model on your training, and then you use your validation set to validate it. And this is very important because if you use the training set that it had learned on to predict how good your model is, that's not good. That's like if you were taking a Microsoft certification exam and you spent 2 weeks retaking the same exam every single day and you were getting 100% by the end, you'd probably still bomb the real one because you just memorized the answers. So that's overfitting. The only problem with this is the only predictions that are really valuable are your validation set. So if you have a really small data set, this is not good. And usually you have really small data sets because data is precious and business users don't always like to get... Usually either you have so much data you're drowning in it or you have a very small amount of data. So to get around that, you use k-fold cross-validation. We'll do more with this next time, but just a quick introduction. You basically break your data set into 5 elements, and you've probably seen this from other machine learning classes, but you break the data into 5 of these, and then you literally create 5 models, 5 neural networks. For the first one, that fold 1 becomes your validation. For the second one, your second fold becomes the validation. So you literally do this 5 times, so it takes 5 times as long. But now you have a validation set. Each piece of the data frame gets to be a validation set once, and you can generate out-of-sample reliable predictions for your entire data set. And that's very, very valuable. We'll see a lot more about this in terms of how to do that. There is a question in the first one that just asks you to break up the data and get it into that form. We're not actually training anything yet. So then literally you have out-of-sample data literally for everything. And this does show you literally the code to do this. This is where you use scikit-learn. Scikit-learn has k-fold, so it will literally split your data set up for you. You just tell it you want to have 5 folds, and it does that for you. And then you can basically print it out. So you can have your 5 folds. That's the size of the training set. Due to the fact that everything just doesn't break up evenly, you don't have even numbers in each one of these. But you can see that the validation set is smaller in each one of these. The training set size is that.